Let's now have a look at the process of single particle analysis. What we're trying to understand is how we can get from the 2D cryo-EM micrographs that we have collected that contain many instances of the molecules that we are trying to image to a 3D reconstruction that represents the 3D structure of these molecules. What we need to understand for this process is that transmission electron microscopy images are projection images. And as you can see in this example, a single projection image is not sufficient to infer the 3D structure of a particular object. That means we need to sample many more different orientations in order to work out the true 3D structure. We also need to consider that cryo-EM images are noisy projection images. So working out these relative orientations will be much more difficult than in the clean images you've seen before. Let's have a look at what's necessary to arrive at that 3D reconstruction. Let's start with a PET example and look at a teddy bear face. If we're looking at this teddy bear face from different orientations, meaning we are orienting the teddy bear face in different angles relative to the incident radiation, for each of these different orientations we will obtain a unique projection image. You can see that in this example. So that means that if we can work out the relative orientation of these projection images, we can probably also do the inverse of that operation. But first, it is essential to note that every unique orientation of a 3D object generates a different projection image. Now, once we know this, we can then, and if we know the relative orientation of these projection images, we can simply do a back projection. So that means we are undoing the transmission electron microscope imaging process by essentially propagating rays through the projection images in the direction of their projection, inverse direction of their projection. As you can see that if the sampling that we have is sparse, so if we only have a few of these projection images corresponding to only few unique views, then the quality of this 3D reconstruction will be very poor, and the reconstructed object will only remotely resemble the original 3D object that we were trying to reconstruct. Now, as we are increasing the number of views, as you can see here, so the unique views that we have of this 3D object, we improve the reconstruction quality. With only 5 views, we can already reconstruct an object that roughly represents the core features of our teddy bear face. We see the ears, we see the nose, and we see the round face of the teddy bear. With 10 views, we are improving the detail. With 20 views, we can already start to recognize the actual object. And with 50 or 100 views, we are getting very close to in reconstruction quality to the original 3D object. So that shows you that increasing the number of unique views improves the 3D reconstruction. And in our cryo-EM experiment, the same holds. So the more different views of the molecules that we are trying to image we can obtain in our cryo-EM micrographs, the better our 3D reconstruction will be. Now, there is another way how we can perform this reconstruction. Instead of doing ray propagation in real space, we can also represent our projection images in Fourier space. So if we're starting out with different orientations, again, of our teddy bear face in real space, we will get unique projection images from those. These are 2D representations of the 3D object in real space. And then for each of these projection images, we can compute a Fourier transform, which means that we are representing the image by its constituent waves and their respective amplitudes and phases. And that means that all unique projection views can also be uniquely represented in Fourier space. Now, if we know the relative orientation of our projection images, then a theorem called the central section theorem states that the Fourier transform of these individual projection images is a slice through the 3D Fourier transform of the 3D object in an orientation perpendicular to the projection direction of the projection image under consideration. So that means if we know all the different orientations of our projection images, we can place their corresponding Fourier transforms into the 3D Fourier transform in the correct orientation, and then perform an inverse Fourier transform to obtain a 3D reconstruction of our object in real space. And again, as you can see, the more unique projection images, and therefore the more unique Fourier transforms we have available, the better the reconstruction quality becomes. Now let's go back to our cryo-EM images. What does all of this mean for reconstruction of our molecules of interest? You should now understand that in this cryo-EM micrograph that we have collected many 2D projections, individual 2D projections of the molecule of interest. So our task basically is to work out the relative orientation of all of these 2D projection images and then feed them back in either of the two 3D reconstruction processes that we have discussed. And together, that should give us a faithful representation of the 3D object, the 3D molecule that we have tried to image. Now, in a single particle workflow, this looks like this. So what we are doing is we are collecting micrographs, transmission electron micrographs of molecules that are suspended in a thin layer of vitreous ice, which we assume to be in random orientations. That means that if we select the individual 2D projection images for each of these particles and we work out their relative orientations, we can place them back into a 3D transform and obtain an initial 3D model. Now, as we are proceeding, we can use this 3D model to generate references to which we can align our original experimental images to improve the angular assignment, and in an iterative fashion, this improves the 3D reconstruction process, such that eventually we obtain a final 3D reconstruction that corresponds to the Coulomb potential map of the molecule of interest, and we can use that map to interpret it in terms of an atomic model.